What's up, CTM students? This is lesson 12.9. In our previous lesson, we learned about permutations, and today we're going to learn about combinations and how they're related, how they're different as well. So permutations and combinations, two very important ideas in probability. Let's check it out. Let's see what we got here. So let's start off with the definition of combination. What is a combination, and how is it different than a permutation? A combination is this. It's a distinct group or set of objects, and here's the key part here: without regard to their arrangement. Without regard to their arrangement. Without being the key word. So without regard to their arrangement. What does this mean in terms of permutations versus combinations? Let's make a little chart like this that'll stand out nice. So permutations versus combinations. Oh, to make it even more interesting, versus. Oh, how about that? Versus. Permutations versus combinations. What's the difference? Permutation, order matters. And with combinations, order doesn't matter. That's basically what it boils down to. I guess I'll make that a capital O. Sounds good. Order doesn't matter over here. So we'll see what I mean by that in this next page. And I'm going to bring it to these guys, Larry, Moe, and Curly. You may recognize them, the Three Stooges. And I'm going to use them to help demonstrate the difference between a permutation and a combination. So if we were using permutations, right now I just want you to listen for a couple minutes here as we go through this. What's the difference? How can you know the difference between permutations and combinations? So a permutation formula, we're using this. Let's say I wanted to choose or pick three, of the three people I wanted to pick two. So I want to pick a group of two from these three guys. So a permutation, again, just listen right now. So permutation, I'll write in green just to remind you that this is just kind of listening. Green for go, just go ahead and listen. How about that? So 3 P2, 3 permute 2, we've got, that would be, according to this formula, 3 factorial over 3 minus 2 factorial. So this would be 3 factorial over 3 minus 2 factorial. In other words, that's 3 factorial over 1 factorial. 1 factorial is just 1, and 3 factorial would be 3 times 2 times 1. So you have 6 possibilities. 6 over 1, which is just 6. With permutations, it's going to be that. But with combinations, what's the difference between permutations and combinations? So let's talk about that right now, where order matters with permutations and doesn't matter with combinations. So let's say I'm picking a group of two. Let's say, just for argument's sake, I picked Larry and Moe. Permutation wise, that would be, I could call that L and M. I'll just label it like that. So L and M, that's one possibility. This is still going to go with permutations. Another possibility is to switch those guys around and say, okay, now Moe and Larry. If order makes a difference, this is a completely different thing. But if order doesn't make a difference, L and M ends up being the same as M and L. So with a permutation, these two things are different, and we count them twice. But with a combination, this is the same combination. Moe and Larry is the same combination as Larry and Moe. So we would only say, you would only count one of those things. That Moe and Larry counts as the same thing. And so these are different. You'd have two different things. You could also have, you could go with Moe and Curly, or Curly and Moe, and you could go with, so again, these are different. These are different. With permutations, the order makes a difference. What else we got? We've got Curly and Larry. So you could go Curly Larry or Larry Curly. But with combinations, Larry Moe is the same as Moe Larry. Moe Curly is the same as Curly Moe, and Curly Larry is the same as Larry and Curly. So combinations, there's only 3. And so the formula is a little different, and it includes less things. So combinations, in this case, we'd have 3, and permutations, we'd have 6. So listening, strictly listening, is over. Let's write a few things down here. Let's check out our first example. So I want you just to decide whether order matters or not in these situations. So permutation or combination. See if you can pick the right choice. Permutation or combination. Let's say you were selecting a class schedule. Would order make a difference when you're selecting a class schedule? I would argue yes, because if you had geometry first period and biology second period, that's going to be a different schedule than biology first period and geometry second period. Yeah, you're having the same classes, but your schedule is different. You're going to different places at different times. So I would say on this one, order matters. Therefore, I would say permutation. So if order matters, it's a permutation. If order doesn't make a difference, it's a combination. How about this? Selecting. What is that? Selecting. It's selecting. Just trust me on that one. Selecting a group of students from a class. Permutation or combination. So if you're selecting a group of students, you could pick 3 kids. It doesn't matter what order you put them in, it's still the same group. So order does not make a difference. If you're just selecting a group of people or a group of students from a class, or a group of people from a larger group of people, this would be a combination. Order does not matter. Okay, if you want to write that underneath, you can, but we've decided that, we've said that over here already. So why are these permutations? Order matters. Why are these combinations? Order doesn't matter. So here, order does not matter. Let's say you had selecting lottery ticket numbers. Man, I'm not writing selecting very well. Selecting lottery ticket numbers. And I've got a copy of a picture of a lottery ticket over here. So if you picked 17, 20, 27, let's say it's a 5 number one. If you pick those 5 numbers, does the order in which you pick them make a difference in terms of if you win it or not? No. Unless this is a special kind of lottery. You could circle 27 first, and then you could circle 17, and then you could circle, I guess there's more than one 17 here, I didn't see that before, but you could circle another one and another one. The order wouldn't make a difference. You could circle this one first, second, third, or this one first, second, and third. You're picking the same group of 5 numbers. So selecting lottery tickets, order does not matter. When you're picking those numbers out, you can pick the numbers in any order. Therefore, it would be a combination. And then how about one more, just to see if you got it down. Selecting let's say an arrangement. Selecting an arrangement of books on a shelf. And that's what I've got going on right here. What would that be? I would argue that the order is going to make a difference. You could put this book here, or here, or here. It's going to be a different arrangement depending on where you place it. The order will matter in this case. Therefore, I would say that's a permutation type problem. So permutation versus combination. In this lesson, they're generally going to be combinations, but on your test in the future, you're going to have to determine what's what. So you're based on the situation, first ask yourself, does order make a difference in this case? If it makes a difference, it's a permutation. If it doesn't, it's a combination. So let's check out the combination formula next. We had a permutation formula. Sure would be nice if there was a combination formula. Oh, there is. Don't you worry. There is. Beautiful. What is that formula, though? Tell me, Mr. Wagner. I'm dying to know. Patience, 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 young one. Okay. The number of possible combinations. I guess you could be older than me and watching this too. So, young one, old one, whoever you are, peer, same age as me. Number of possible combinations. What am I writing? I don't know why I wrote possible twice on my notes there. Number of possible combinations. There we go. When our objects are selected from n objects. So we're going to use R and N again, just like before. And it's going to look really similar to what we had here. So it's going to be N, but now C for combination instead of P for permutation. And then we'll see what the difference is between this. You're starting with the same basic formula. We're adding one extra thing into it. So this will be written as N, and then a C, and then an R. So N, I'm used to saying N choose R. I think that is technically correct. I'm going to have to look that up later. But N permute R versus N choose R. So N choose R is what I'm saying for right now. That would be N factorial over N minus R factorial. Well, hold on a second, Mr. Wagner. That looks exactly the same as permutation. Did I say I was done? No, I didn't say I was done. Hold on. So yes, it starts the same, but you want to get rid of a few more. You want to get rid of the ones that are all the same, just in a different order. To do that, you could also, or you need to also divide by R factorial. So the number of different ways you can arrange the things you're choosing. If you divide by that factorial, that gets rid of all the duplicates, you might say, or the same choices but different orders. So that, by doing that, you get rid of that. Let's write that down in a different color. Let's write that off to the side. So this is the difference, the R factorial. The extra R factorial is the only difference between the formulas for permutations and combinations. So here it is there, here it is here. This gets rid of duplicates in different orders. If you can understand why formulas are the way they are so much easier to remember. So I'm trying to help you understand why this formula is the way it is, rather than just try to memorize a bunch of weird looking letters altogether. So that is what we have. Let's use that for some more examples here. So let's say this is the situation. Your teacher, hey, that's probably me. Your teacher has put you into a group of 5 students. So let's say that's true to start. You got a group of 5 students and is randomly selecting a pair of students. If you see the word pair, you should think 2, so 2 students, in other words, a pair of students. Apparently you're given some presentations here because they're going to speak on your group's behalf. So to speak on behalf of your group. How many ways can this pair be selected? Question mark, question. That is the question. So what's our solution? How do we solve something like this? So we've got a group of 5 students. Let's write that off in a different color off to the side here. Pair, that's 2. So you're having here, the order is not going to make a difference, because if you pick Johnny and Billy, that's the same as Billy and Johnny. That's the same group of 2 students. If you pick Susie and, I don't have a name coming to me right now, Susie and Byron. Let's go with Byron. Susie and Byron, that's the same as Byron and Susie. So let's say we've got, or we know we have a combination problem. So we're going to have 5 choosing 2. So 5 choose 2, use the formula now. So go back to the formula. We can use this to figure it out. So So what goes on top? That's n factorial. That's the first number factorial. You could say, I got to bring it back at least once. 5! 5 factorial. Okay, you can say 5 factorial. This would be 5 minus 2 factorial. And then you have this now. This would be a permutation. So if order did make a difference, that's what you'd do. But since order does not make a difference, we need to get rid of those duplicates by also multiplying by, or dividing by, sorry, 2 factorial. So we're also going to have 2 factorial. If you write factorial next to a number like this, we can assume it's multiplication in between. If you want to add the dot in there, if you wanted to write it like that, you could. But if you leave that out, just assume multiplication in between there. So from here, what are we left with? We are left with, we have 5 factorial on the top here, and we've got 5 minus 2 factorial becomes 3 factorial. So I don't need the parentheses anymore. So 3 factorial and 2 factorial. I'm going to show you the long way on this one and show you the shortcut ways on some of the other ones. So this, written out the long way, would be 5 times 4 times 3 times 2 times 1. On the bottom, you've got 3 times 2 times 1. That's 3 factorial, that's that part. And then this times 2 times 1 is the 2 factorial part. Now here's how I would cancel this. Let's get out the different color for our cancellation. 3 times 2 times 1 would cancel out with the 3 times 2 times 1 on the top up here. What are you left with? Looks like 5 times 4 over 2 times 1. You can reduce farther before you finish this up, or you can finish this up after you reduce farther. So a 2 and a 4, I could replace that with a 2 and a 1. That's as much simplification as I can do. So that leaves me with 5 times 2 on the top, 1 times 1 on the bottom. That gives you 10 over 1, which just equals 10. So how many ways can this happen? 10 ways. Give a word describing what you're talking about to finish that up. Alright, let's move on to a third example. This is a poker example. So this is some different poker hands, but my question to you is, how many are there actually? How many different poker hands could you have? How many possible 5-card poker hands can be dealt from a standard deck? So let's go ahead and solve that. Let's see what we got. So this is, well, how many cards do you have to pick from? How many cards in a standard deck? You have 52. So you have 52, and then you have 52 choosing 5 cards. Of those 52, you're going to pick 5 cards. So does order matter? Would an ace, king, queen, jack, 10 be the same as a jack, king, 10, queen, ace? Yeah, the order's not going to make a difference. So because of that, we have this with this problem. We have 52 factorial over the n minus r factorial would be 52 minus 5 factorial, and then don't forget to multiply that by r factorial. So multiply that on the bottom, it's this divided by all that together. Now the shorter way to do this, 52 factorial, let's write this first, 52 factorial over 47 factorial times 5 factorial. That's what we have to start. Now this is the same thing as saying 52 times 51 times 50 times 49 times 48. Are you serious, Mr. Wagner? We're going to go all the way down to 1? No, 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 no. Stop right there. I notice there's a 47 factorial down here. So 52 times 51 times 50 times 49 times 48 times 47 factorial means to go all the way to 1. So I could stop right there and watch what happens. So if I have 47 factorial times 5 factorial on the bottom, take out your different color, cancel that, and cancel that. Gone. Sweet. So we're just left with 52 times 51 times 50 times 49 times 48 over 5 factorial. Let's expand 5 factorial now. So at the bottom you've got 5 times 4 times 3 times 2 times 1, and now reduce as you see fit. So what I see here is I noticed that 4 goes into, of these numbers, I noticed first that it went into 48. So I'm going to say this is going to become a 12, and this would be a 1. 4 goes into both of those that many times. 5 goes into 50, so I could say this is a 1, and that this would become a 10. 3 would go into 51, and so I could get rid of the 3, make that a 1. This would be 17. 51 divided by 3. And then 2 and 52, I could reduce that. 26, this would be a 1. So that leaves me with just 1. 1 times 1, 5 times itself 5 times. That's just going to be 1. So you have 26 times 17 times 10 times 49 times 12. You have all this over 1. So the 1, you cannot think about that anymore. You don't need to think about that. This becomes, if you multiply this in a calculator, I double checked carefully on this one. I know this is right, so I'm just going to do that without getting out my calculator. It's 2,598,960 hands. And so if you've ever watched poker, maybe on ESPN, something like that, they're showing you the probability of somebody winning the hand. They're using all these different possibilities, and they're calculating, the computers are calculating it very quickly, figuring out what's the possible hands that they could get with the, if they're playing Texas Hold'em style poker, what are the possible hands that you could get, and what are the chances of drawing a certain card, and it does all those calculations at once. But this is the basics of that, or the beginnings of those calculations are in here in this combination idea. Alright, let's check out a fourth example. Now that you know a little bit more about poker, I don't know that much about poker myself, but it's kind of fun to play, just for fun. I don't like to bet too much, but just playing with chips can be kind of fun. Let's see, how many different committees? The last one, we're going to form some committees, or form a committee. How many different committees can be formed from, going back to school again here, so from 6 teachers and 50 students. If the committee is to consist of two teachers and 3 students. So it's going to be a 5-person total committee. But what do we got there? What are we going to do? So you have 6 teachers to choose from. From those 6, you are going to choose, you are going to pick 2 of those teachers. So one part of this should be, should be 6 choose 2. You should read it like that. So that's the teachers part. Let's put that in a different color above that there. So this is teachers, and then how about for students? What are you going to have for students? That would be 50 students, and you're picking or choosing 3 from that group of 50. So this is the students part. And what do we do? What do we know we can do with probability? With the counting principle, we can multiply these things together. So what's the chance of getting, or how many different ways are there to pick a group of teachers? And then how many different ways are there to pick a group of students? Multiply them together, and you got how many different ways there are to pick both the teachers and the students. And so let's see what these things equal. So 6 choose 2, that would be 6 factorial over 6 minus 2 factorial times 2 factorial. And we have that times, and then you'd have 50 factorial here over 50 minus 3 factorial times 3 factorial. And we'll use this shortcut way again here to make life simpler. So you have 6 factorial over 4 factorial times 2 factorial. You have this times 50 factorial over 47 factorial times 3 factorial. So we can write this 6 factorial as 6 times 5 times 4 factorial. And you can have that as 4 factorial and 2 factorial. This would be 50 times 49 times 48 times 47 factorial over 47 factorial times 3 factorial. Writing it like that, let's take out the different color there. That reduces, or that cancels with that. That cancels with that. That makes it a lot easier to deal with. And so from there, I'm going to just say I'm going to continue this up here. You probably have more space in your paper. I want to keep this all in the same place though, so I'm going to just continue that up here. This would become, or this would equal, 6 times 5 is what's left on the top. You've got 2 times 1 on the bottom. Then here you have 50 times 49 times 48 on the top over 3 times 2 times 1 on the bottom. So let's cancel what we can here. This is going to become, you could go with a 3 and a 1 right there, so all 1's on the bottom. Go away page browser. Bye, thank you. Okay, and 3, that would be, we could say that would reduce with that, with a 1 and a 16, and that way this would be, you could go 1 and 25 right there. So what are you left with here? You've got 3 times 5 over 1, so you don't need to write that. So 3 times 5, you've got that for your teachers, and then you have what's left over here. You got 1 on the bottom, so I don't need to include that. It's just 25 times 49 times 16. This is 15 times, and if you multiply this together, you should get, I want to double check this one just to make sure. You should get 25 times 49 times 16 is 19,600. So a lot more ways to pick the students, and the teachers should be expected that there's 50 students to choose from. If we take that number times 15, we get 294,000 committees. Those are the number of possible committees with that many students and teachers to choose from if you pick 2 teachers and 3 students. Are there easier ways to figure this out before I close here? Are there buttons on your calculator that can do this? If you have a good scientific calculator or graphing calculator, definitely. So I'm going to require you to know how to do this without a calculator, but there will be times when I say, okay, you can just plug the 6 choose 2 in a calculator and tell me what that equals and go from there. So we need to get good at this. That's why I've practiced that in this lesson with you. You will, I'm thinking, at least at this point, that you will on the test for my class. You'll have to do some stuff without a calculator, and then other stuff you'll be allowed to use a calculator. So make sure you know how to do that. Make sure you got the longhand way down before you learn how to do that in the calculator. Any questions, you let me know in class if you're one of my students. And hey, have a good day. I will see you later.